We're going to talk about 8.4 and 8.5 today. 8.4 is areas of regular polygons. 8.5 is areas of circles. 8.4 is something that you may have seen before, but a little bit more difficult than the circle stuff that you've dealt with in the past. So let's get started. We start off by one way that we can create a regular polygon is if you have a circle and we cut it into 6 central angles, 6 60-degree angles, and then we connect up all of our uh, we connect up each of the central angles with chords here. We've formed a hexagon. Now, if we wanted to find the area of the hexagon, what we've got here is isosceles triangles. So what do we need to know in order to find the areas of an isosceles triangle? Well, we probably want to know the height of the triangle, which is here, and we probably want to know the base of the triangle as well. So if we have the base and we have the height, we can find the area of the triangle by 1/2 times base times height. Then if we want to find the area of the hexagon, what we could do is, since there's 6 of them, there would be 6 1/2 times base times heights. Now this 6 is the fact that it's a hexagon, and since we're dealing with polygons, we're not actually talking about just that being a 6. So when we take a look here, we'll be looking for this guy right here for all of these, and then each of the bases, 1, 2, 3, 4, 5, 6, that's going to be the perimeter of the figure. So instead of doing 6 bases, we can do the perimeter of the figure. So if I know that I have the area would be 1/2 times the perimeter of the figure, that's going to be all of the bases together if we wanted to do all the triangles at once. And then it's times the height of each of the individual triangles. Now, this isn't really a height on a hexagon or on any polygon for that matter. It's actually called the apothem. So we're going to change that H to an A. So on your chapter 8 term sheet, and also I think it's on your day 2, which you should have your day 2 right now. If you don't have it, let's make sure that we get that. You might need to pause it and grab that. To find the area of a hexagon, then we're talking about this guy right here, which is the apothem, and if we know the perimeter, the distance around, we have a nice formula, because we're just finding groups of, and it's not just for a hexagon, it'll be for any regular polygon inscribed in a circle, for any regular polygon for that matter. Here's our formulas. Okay, let's take a look at what these mean. First of all, the apothem, or A, that's going to be the perpendicular segment from the center to a side of the polygon. So that's going to be, this is a right angle distance. Notice this will, since it's coming out of the center and forming a right angle, it has to be perpendicular. That came from chapter, I believe it was 6, which talked about our chords and things like that. Maybe it was chapter 5. I'm sorry. We have area 1/2 times the apothem, that's like the height of the triangle, times the perimeter, that's like all the bases at once. So this is a pentagon here, but this will work for any regular polygon. Sometimes we want to break it down depending on what we're looking for. Perimeter is equal to S, the side length, times N, the number of sides. So we have S, the side length, and the number of sides. In this case, it's 5. So this right here is just a simple substitution problem. I kind of prefer to use the 1/2 times A times P, and then we all should know how to calculate a perimeter. And then if we're looking for the number of sides or something like that, we can work backwards with this little formula right here. So A equals 1/2 AP is going to be our formula that is going to be the most important thing for 8.5 regular polygons. Also, like most of the things we've done in this class, it'll come up again and again in what's going on. I believe this problem is on the back side of day 2, so why don't we go ahead and grab the back side of our day 2, and we will calculate a bunch of different things. We do need to think about some other stuff. Each angle of a regular pentagon is, remember, if you can't remember how to find the each individual angle of a regular pentagon, it's n minus 2 times 180 divided by n. And in this case, it would be 5 minus 2 times 180 divided by 5. And for a pentagon, it's 108. Many of you probably already knew that. Let's take a look at what that looks like when we draw this guy here. So if I drew that in, I have a right triangle, and then I've got my apothem, and I have, these are each 108 degrees, and this would then have to be 54 degrees right there, and then that's a right angle, and this would have to be 36 degrees. Might be useful to us at some point. They're also asking us for each central angle formed by the apothem and the radius of the circumscribed circle is, and we just said that it was 36 degrees. That's the apothem, and that's the radius. We call it the radius of the circumscribed circle. This is also called the radius of the pentagon here. Area of the regular pentagon will be area equals 1/2 times the apothem times the perimeter. In this case, the perimeter will be 9 sides, and there's 5 of them. 9 times 5 is 45. So the area is going to end up being 45 times 4. My area is 180 centimeters squared. Okay, 1/2 times the apothem times the perimeter. Next one, this is also on there. It looks like this is a regular heptagon. 1, 2, 3, 4, 5, 6, 7. First thing they want us to do is calculate each angle of the regular heptagon. N minus 2 times 180, that's 5 times 180, and then divided by 7. Each of them is 128.57. I know the 7 makes it into kind of an ugly problem. Whenever you're dividing by 7, good things never really happen. Let's just go with 128.57. Again, each angle formed by the apothem and the radius of the circumscribed circle is, well, if you think about where we're getting that information, we're going to go right here, and we're looking for this little angle right there. Okay, which means if this whole thing is 128.57, then this one has to be half that. So we take our 128.57 divided by 2, 64.3. Let's go with 64.3. And then if that's 64.3, this one has to be 90 minus 64.3. We also could form the central angle from the two radii, because we have an isosceles triangle, of course, with the radii. That would also work. So 90 minus 64.3 must be about 25.7, if I did my math correctly, which is entirely possible that I made a mistake. Area of the regular heptagon, area equals 1/2 times the apothem. Uh-oh, I don't have the apothem. Well, whatever are we going to do? Let's go back up here. If this is 12, this guy right here has to be 6. What am I talking about? That's 15. I was thinking the radius was 15. Oh, you can stop yelling at the TV right now, or the computer screen. 1/2 times 15 centimeters times the perimeter. 12 times 7. I think the last time I checked, 12 times 7 was 84 centimeters. So when we put those guys together, we should get 630. So this is going to be 630 centimeters squared. I would imagine there's problems coming in our future that the apothem is unknown, and we'll have to use either the angle measurements or the hypotenuse, which is the radius of the right triangle. Here we have the apothem is 14.5. Side length is 12. Find the area. Area equals 1/2 times the apothem times the perimeter. 12 times 1, 2, 3, 4, 5, 6, 7, 8. It's an octagon. 12 times 8 is 96. 1/2 times 14.5 times 96. is 696. And these would be centimeters squared. Again, make sure that you're labeling properly. Okay, we got a little bit different problem here. Now we know the perimeter and we're working backward, or we don't know the perimeter. We know the area, we know the apothem. So we start with area equals 1/2 times the apothem times the perimeter, and we can work our way backwards. 130.8 equals 1/2 times the apothem times the perimeter. And we need to solve for P. 130.8 equals, I'd put these two together, 3P, and now we divide by 3 on both sides. 130.8 divided by 3 is going to be 43.6. 43.6. So we found the perimeter to be 43.6, and then if we really wanted to go a step further and figure out what is each individual side going to be 43.6. I had 5 sides. This was a pentagon. 5 times the side length. So I can take 43.6 divided by 5 and get 8.72. So this was a pentagon with side lengths of 8.72. 8.72, that's a 7. So they asked us for the perimeter, which was 43.6 centimeters, but we also found the side length to be 8.72. So make sure you keep track of what they're asking for. You can work backwards, just like the rest of it. Okay, so that covers the 8.5 stuff. 1/2 times the apothem times the perimeter are going to be used a lot extensively from now until January 16th, which is not only my birthday, but it's also the end of the semester. Area of a circle, this is one that we should probably already know. It's pi times the radius squared. Please remember that circumference was 2 pi r, which could also be written as pi times the diameter. For our area, we're only dealing with the radius squared, so you have to change all your diameters into radii. Given some quick info here, diameter is 6.4. I would change the radius to 3.2. Area then would be equal to pi times 3.2 squared. Now, sometimes they ask us for our answer in terms of pi. In terms of pi, this would be 10.24 pi. 10.24 pi. If they want you to actually multiply it out, this becomes an approximation of 32.17. Looks like these were centimeters, so these would have to be centimeters squared. So please make note, are they asking it for in terms of pi, or are they asking for an approximated value where pi is multiplied in? They give us the circumference. Don't forget the formula for circumference is pi times diameter. Well, if this is pi times diameter, then the diameter is 36. If the diameter is 36, then the radius is 18. If the radius is 18, then the area is 18. Is going to be pi times 18 squared. 18 squared is 324. So again, the exact value, 324 pi centimeters squared. I could multiply the pi in, and I get 1017.88 centimeters squared. Exact value, decimal approximation. Make sure you read the directions on which ones they're looking for. Again, radius is 7.8. Area would be whatever pi times 7.8 squared is. If I wanted to do 7.8 squared, I'd get 60.84. And I'd have pi, and it would be centimeters squared. If I wanted to multiply the 60.84 times pi, utilize the calculator, and 191.13 centimeters squared. Give me a diameter. Cut it in half to get the radius. That's a common mistake. People just get too antsy and want to get on with the problem. Don't forget you need to find the radius. It's 1.56 first, and then we're going to square that and get 2.4336. And then if we wanted to multiply that times pi, we get 7.65 for my area.